Okay, so last time we left off, we had an exercise, which is compute the singular value decomposition of x. So I've been sort of jumping between the SVD of x transpose x and the SVD of x. Really, what I wanted was the SVD of x, since we're just looking at the singular values, we really only care about the square root of the absolute value of the singular values. We only are going to care about the square root of the eigenvalues of x transpose x. So there's two ways to go about doing this. We'll just see one of these ways. Okay, so we have our different rows. This is our list of rows again. And what I'm just going to do is let's append to this list the singular values, which is this D here, the singular values of x. Right? So we're going to compute the SVD of x, take the D singular values, and then we're going to append to this matrix the singular, or to this list, the singular values. And this is, we can think of this as a matrix because each of these elements is a one-dimensional array. Okay, then I'm just going to create a different color for each of the rows. There's a number of ways in which you could plot this. This is the simplest in my opinion. So we're going to create one color for every row, and then we're just going to plot the eigenvalue index and the singular value from largest to smallest. Okay, so I've been a little bit cavalier. Oops. There you go. I've been a little bit cavalier about calling these singular values versus eigenvalues. These are singular values. What I've computed here are singular values. The eigenvalues are the squares of these singular values. It's very important to make this distinction clear. So this still is the index. These singular values are ordered from the largest to smallest. They start at some large number and typically get small. So when row is 0, we see that all of these singular values are roughly flat. They're all around the same value. But once row starts to increase, then what we see is that the 0 singular value is typically very large, and then it gets smaller. And as row gets larger, closer to 1, this smallest singular value gets much closer to 0. And if you know anything about, if you think about what the covariance matrix is for the x's in this case, then you know that it has this large rank 1 component, and then it looks like the identity mixed with this large rank 1 component. So this actually really makes sense, what we're seeing here. Okay, and so what does this mean? So I said before that because the singular value gets inverted, the small singular values are going to make our ordinary least squares betas pretty unstable, right? And we see that here, that we have a lot of very small singular values, and that's going to create instabilities in our betas, right? And so that's just like what we had before, that we had correlations between the columns of x corresponded to instability, created instability in the beta hats. And in this case, we see exactly the same, we're going to see exactly the same thing, but now it manifests itself through the singular values. Okay, so what can we do about this instability? Well, typically we regularize in the presence of such instability if we really want that this beta hat is more stable. Now, it's not necessarily the case that having an unstable beta hat is a problem. Right before, we had this situation where we duplicated our x's. This was one of the first exercise in this lecture. We duplicated our columns of x, and the beta hat changed, and it actually was no longer unique. No longer had a unique solution to the normal equations. But if you look at every solution to that normal equation, had the same y hat. So it has the same prediction. And so the predictor actually doesn't change no matter what the beta hat is. So this is something that has to do with what we really want to get out of our linear regression. Do we want something that's actually, do we want something that is giving us stable beta hats, or do we want something that gives us good predictions? Because if all we want is stable beta, if all we want is good predictions, then actually in some situations it doesn't matter whether our beta hat is unstable or not. And maybe we'll be able to come back to this much later on in the course when we talk about interpolators. Okay, so ridge regression. Ridge regression, the basic idea is that we're going to compute our least squares, the minimizer of our square error loss, right? So we have that this sum here is proportionate to our empirical risk. But instead of just having our empirical risk here, which is the sum of our square error losses, we also have another term, which is a sum of the squared betas. And typically in this situation for ridge regression, we omit the intercept term, which is beta 0 in my notation, which is why I have j ranging from 1 to p. And then I multiply this sum of the beta j squareds by lambda. And the effect is that it's going to try to pull this beta towards 0, right? That's what this naturally is going to do. We penalize beta solutions that have large beta squareds. So that's going to pull it towards 0 and bias us towards 0. Ridge regularization now is going to pull beta towards 0, right? And lambda is a tuning parameter which determines how much it gets pulled towards 0. So for example, in one extreme case, lambda could be 0. Then we just have ordinary least squares. In the other extreme case, lambda is infinity. Now beta, the solution is beta equals 0 because the ridge term is going to dominate this square error loss term. Okay? So that's one thing. The other thing, typically when we do this, we have to center and normalize our x. The reason for this actually can be quite intuitive. If we have a centered x for all but the intercept, then we have that all of our x's, then we have that beta hat 0, this should be beta hat 0, is just equal to y bar. Then we can remove the intercept from y and perform the ridge with beta without the intercept. So we can actually think about fitting an intercept as just centering our x's and then removing beta hat 0 from the equation just by setting beta hat 0 equal to y bar, right? Sorry, this should be a 0 right here. So typically we think of our x's as centered, our y as having y bar removed from it, and now because we've centered x and y, we can pretty much just ignore the intercept. So throughout this course, I'm going to kind of treat the intercept as this nuisance that I just brush to the sides by centering everything. Now, with x, another thing is that typically now it really matters if we normalize x, right? And so what I mean is that after we've centered, we divide it out by its 2 norm, which is its empirical standard deviation. And the reason for this is if you look at the penalty, it treats all the betas the same, right? But say I multiply the x by some number, like 100, for one of the x's. Right? One of the components, so one of the columns of x, I multiply it by 100. Now beta, to get the same effect, is going to be divided by 100, right? To have that your x times beta for that single beta stays the same, right? So beta gets divided by 100, but this penalty doesn't reflect this change in scale of beta, right? And so, to make sure that they're all at the same scale, you make it so that all of the x's have the same norm, and you just do that by dividing out by the norm of the column of x. So that's another caveat, is that typically this is in centered and normalized x's, so it really matters in this case to standardize our x. We already saw that it mattered to standardize your x for k-nearest neighbors. Now it really matters for ridge regression as well, and most other penalizations or regularizations, it really matters to have a standardized X. Okay, so ridge regression. Another way that we can write it is just this y minus x beta transpose itself, right? That's just the sum of squares, right? Because it's the 2 norm of y minus x beta. And then the ridge term, we can write it as lambda times beta transpose beta. That's the sum of the squared entries of beta. This is after we've standardized our x. Now, if we think about this objective, it's proportionate to this cross term for this first part is minus 2 times y transpose x beta. And then we add in the second term here, this beta transpose x times beta. Now, I would encourage you to have a notepad verifying this math just by doing the FOIL, I guess. And then we still have the ridge term. Notice that I'm omitting the y transpose y term. That is a constant in beta, so it doesn't matter. Okay, so now if we look at this, we look at what happens if we set the subgradient equal, or the gradient equal to 0 for this objective. It's going to give us a normal equation, but now it's augmented by this lambda times the identity, right? Because we have this beta transpose x plus lambda I times beta. And this is the effect of regularization. Effectively, all it does is in the normal equations, it adds a little bit of the identity to this x transpose x. Right? Now, one nice thing about this is that this ridge regularization always has a solution because this x transpose x, a unique solution, because this x transpose x plus lambda I, the inverse, exists. So it always has a unique solution because of this. So that's actually one really nice thing about it, and it's why we call it regularization. It gets rid of these issues of correlated x in terms of the solvability and having a unique solution. There's a bit of a caveat. It is biased in some sense, and let's talk about what this bias means. So by bias, we mean that if we think about a linear model, the sort of linear model that you would want to be solving with something like ridge regression or ordinary least squares, this linear model is yi, is the observation, is equal to xi transpose beta plus epsilon I. And this is going to be our model. So we're going to just assume that this is the case where epsilon I has a conditional expectation of 0. Okay? Now, one way that we can write this is that y is just equal to x beta plus epsilon, where epsilon is a noise vector. So if we look at beta hat, the ridge solution for beta, look at its expectation after we condition on the design, x, then we can just write out what the solution is. That's x transpose x plus lambda times I, inverse x transpose y. X is fixed because we've conditioned on it. This is equal to the expectation of x transpose x plus lambda I inverse, now times x transpose x beta, because of our model for y, plus another term, which is epsilon. Now, epsilon, remember, it had conditional expectation of 0, so this part's going to go away, because x is fixed. We have some matrix multiplying something that has expectation 0. That just has expectation 0. The other term is this x transpose x plus lambda I inverse x transpose x beta. And because this lambda is non-zero, this inverse is not going to exactly match this x transpose x. If this lambda was 0, then we would have x transpose x, if it was invertible, gives us something that's going to cancel with one another. These two are going to cancel with one another, and we'll just get back beta. So OLS in this case is going to be unbiased, but ridge is now biased because this matrix can shrink more than this this x transpose x is going to compensate for. Okay, so let's recall that we could write the OLS solution of beta hat using this Okay, so this leads to our next exercise. Sorry, I was interrupted. This leads to our next exercise, which is that we recall that our OLS solution has this following form. Now let's consider the solution to the ridge version of the normal equations. Instead of the standard normal equations, let's use this ridge version. Now, I'd like you to take the SVD of X and show that there is a similar form to this OLS solution that I have listed here, but now for the ridge normal equations, that there's a similar thing. And just as a hint, the similar form should differ on this diagonal matrix that's in the middle. So this is D inverse. It should change, and now you can think about ridge regression as augmenting the singular values in this OLS solution. Okay.